Hi, I'm Adolph Oliver, and in this lesson we're going to talk about real numbers. Now, you've probably not given much thought to numbers in the past or different types, but there are different varieties of numbers, and when you get all the way up to statistics, it'll play a central role in what type of analysis you can do depending on what type of numbers you have. So this whole idea of what numbers are is a developing story for you as you go further along in your math. Well, let's start out with the beginning, what numbers were first used for, and that was for counting things. Somebody had to keep track of how many sheep he had in his flock, and so he just started counting 1, 2, 3, and so forth. So the natural or counting numbers, simply we can start making a list as we count 1, 2, 3, and then we can give the 3 ellipsis dots, which indicate that the pattern continues on like that. So when you think of natural numbers, think also of their other name, counting numbers. And simply, if you'd count something, you'd start with 1 and then go to 2 and 3 and continue on as far as you needed to. Now, the next thing up are what are known as the whole numbers. And the whole numbers are just like the natural numbers, except with the addition of 0. So the whole numbers would start 0, 1, 2, 3, and then of course go on as high as you needed to. Now, 0 was a very important invention because remember, we have decimal numbers, and if we want to be able to tell the difference between, for instance, 502, 520, or even just a plain 52, we need to have a 0 to hold a place if there's no value in it. For instance, 520, there's nothing in the ones place, 2 in the tens, 5 in the hundreds, for instance. Okay, so 0 plays an important role as a number which can indicate to us when we write numbers that that particular place doesn't have any value. Okay, well, next up, the integers. And what we add here are the negative guys. So we could do something like this. Have the 3 ellipsis dots on the left, -3, -2, -1, 0, +1, +2, +3, and the ellipsis dots going off on the right. Okay, well, the integers then include the negative guys, but so far we don't have any fractions or decimals. Well, that changes now when we get to the rational numbers. Rational numbers, you see in the name rational ratio here, and that reminds you then how they're made. As fractions, they are the ratio of 2 integers. Well, integers can be positive or negative like we had up here. So for instance, I could make a fraction 6/3, okay, and that would be a rational number. Now, of course, we know that can also reduce down to 2 as well. You could also have -4/2. Okay, -4 is an integer, and this would give us, for instance, -2. Well, they don't always have to come out as integer values. You could just have something like, 5/3, and there it is. We can't reduce that any. So these are all examples of guys which are rational numbers, and one of the things this points out to us is that you can make rational numbers which reduce down to just whole numbers or counting numbers, and we'll come back to that idea in just a moment. But first off, there's something else to point out to you. As decimals, rational numbers always do one of 2 things. Let's look at a couple of simple examples. 1/4. Now that's definitely a rational number. 1 and 4 are both integers, but as a decimal, we know 1 divided by 4 is 0.25, so this is a decimal that terminates or comes out right on the button in the hundreds place. Well, besides doing that, decimals or rational numbers can always repeat. And so let's look at the classic example, 1/3. Well, if you take 1 and divide it by 3, you know what you get. it comes up to be 0.333, and the 3's, of course, keep going on forever. Somebody came up once upon a time with a bright idea of indicating this as 0.3 with the bar over the top, and that just means that the 3 repeats. Well, if you're going to use this number in a calculation, whether you write the 3's going on continuously or have the bar over the top, which indicates the same thing, you have to round this someplace. So one of the things that we ought to make note of here is that there are certain rational numbers, like 1/3, which cannot be represented exactly as a decimal because the decimal values go on forever if they repeat like this. And what happens is, somewhere on the line, you've got to stop and round the thing. And when you do that, you've got an approximation, but not the exact value. So for that reason, fractions are always going to remain around because the fraction 1/3 nails the value on the button where any decimal representation will not hit it exactly. So let's go over this again. Rational numbers, then, are the ratio of two integers. You can write them as fractions. That's the most common thing. But the fractions that you get are going to do one of two things. They're either going to terminate at a certain place. These guys up here terminated in the ones place. Or they're going to be fractions which repeat and go on. Well, as we saw above here, that 6/3 reduces to 2. That points out that some of these guys, in fact all of them that we've talked about already, are really rational numbers. The rational numbers include all of these guys up here. Why? Well, you could take any counting number and put a 1 underneath it. 2/1 would still equal 2. That makes it officially a rational number, but it's also 2 as well. You can do the same thing with any whole number and also with any integer. So the natural or counting numbers, the whole numbers, and the integers are all examples of the rational numbers, although we often think of the rationals as being fractions, but of course, as we pointed out, you can also take those fractions and convert them to decimals, and the decimals will either terminate or repeat. Well, you might think that after you've talked about the rational numbers, that if you made a number line, okay, and started filling it in, here's 0, here's 1, here's 2, here's -1, here's -2, that the rational numbers would completely fill in the number line. Exactly the opposite is true. If you turn around and just blindly pick any point here on the number line, most often you will not hit a rational number. What's the other things that occur here as well? Well, let's talk about the last type of the real numbers. These guys down here that gave the Greeks fits, they're known as irrational numbers. Now, here's what an irrational number is, basically the opposite of what a rational guy is. Irrational numbers cannot be written as the ratio of two integers. In other words, a rational or an irrational number is impossible to write as a fraction. The other thing is, if you have an irrational number as a decimal, they never terminate or never repeat. As decimals, irrational numbers go on forever, never terminating, never repeating. Well, this is kind of interesting. Let's talk about, I mentioned the Greeks were the ones who first ran into these and had fits with it. They, of course, were interested in what a circle does. And remember, you can find the circumference of a circle by taking pi times the diameter. Well, they kept measuring circles, the circumferences and the diameters, to try and nail down exactly what this value of pi was. They were hoping to get it to be a nice rational number, in other words, a fraction made out of integers, and they could never nail it down. And of course, nowadays we know why. Pi is a classic example of an irrational number. 3.1415927. That's as far as I remember it. But it goes on forever, never terminates, never repeats. Folks have calculated the value of pi out to millions of digits, and it just keeps going. So it's a classic example of one of these irrational numbers. What are other examples? Well, most square roots. For instance, the square root of 2 equals 1.414, and it goes on forever. Now, there are some square roots which have nice answers. For instance, the square root of 9 equals 3. That's a nice rational number. But the square root of 10 or the square root of 8, okay, and either side of it, are not. They're irrational numbers. As decimals, their values go on forever. So, classic examples of irrational numbers, pi, and square roots that don't have nice answers. Now, the square root of 4 would be 2. That's rational. But the square root of 2, square root of 3, square root of 5, those are all irrational numbers. Now, one last thing then. What we've done now is said, okay, what are the real numbers? Well, the real numbers are all of these guys. All of the natural, the whole, the integers, because they're really just types of the rational numbers. But this goes all the way down and also includes the irrational numbers. So, the major groups of the real numbers happen to be the natural or counting numbers, the whole numbers, the integers, which are all versions of rational numbers, which of course include all the fractions and decimals that terminate or repeat, but you also have to toss in all of the irrational numbers. They're the guys that fell out the number line, and classic examples of them are like pi and the square roots that don't have nice answers. Now, one last parting statement about all this business. In elementary algebra, we just work with the real numbers. Well, that implies that there must be some unreal numbers. Well, there are. You'll bump into those in intermediate algebra, but they're not called unreal. When you bump into them there, they'll be known as the imaginary numbers. Okay? And you think, oh my gosh, what's this imaginary numbers business? With a name like that, are they of any use? They certainly are. Imaginary numbers can be used, for instance, to analyze the sound that I'm creating when I'm talking to you. All your fancy little iPods and iPhones and all of that stuff that have music and sound, that can be analyzed by imaginary numbers. Light can be analyzed, electrical currents coming out of the wall, earthquake waves, all kinds of things. And so we'll hold off and not talk about imaginary numbers in elementary algebra, but you'll bump into them when you get to the intermediate algebra. Here in elementary algebra, we're sticking just with the real numbers. Okay, well, now that we've given you an idea of these different types, and remember, it's important to know these because it'll allow us to make different types of analyses as we go along, particularly when you get up into statistics. Let's now look at some examples of these guys. Now, one of the things folks often use letters to represent the different types of numbers. N for natural, W for whole, Z for integer, Q for rational, I for irrational, and of course R for all the reals. Well, what we're going to do is take a look at examples and talk about which ones of these sets or groups they belong to. 11. Okay, first off, let's see, is that something we're going to run into when we count? Well, we would certainly run into 11 when we count, so it is definitely a natural number. Okay, well, remember, the whole numbers are just like the natural numbers, with the addition of 0, so that means this is also a whole number. It's an integer because the integers include both the positive and negatives of these guys, so it happens to be an integer. And we could write it as a fraction, 11 over 1, which means it's a rational number. And the only thing it's not is irrational, because since it can be written as a fraction, that means it's not an irrational. And of course, the last thing that it qualifies to be is a real number. So this is the game we play. Take a look at the number and see which of the groups it matches. Here, 11 fits into everybody except the irrational folks. Okay, well, let's look at 0. Okay. First off, when you count, you don't start with 0, you start with 1. So 0 would not be a natural number, but it is a member of the whole numbers, so we can list it there. And it does show up in the integers. It's right in the middle between the negatives and positives, so it's definitely an integer. We could make a fraction out of it by putting 0 over 1, so that means it's definitely a rational number. Now, since we can make a fraction out of it, that means it's not irrational, but, of course, it's definitely a real number because real numbers include all of these. Okay, let's move on to -5. Here we have our next example. We're looking at the number -5. Now, let's rate it in all of these. First off, you would not run into -5 counting things. You start with 1, 2, 3 and go on up, so it's not a natural number. The whole numbers start with 0 and go on up, so -5 would not be a whole number. But it is an integer, because the integers include both the positive and negative, guys, and so this would be an integer, so we can list that. Next off, we can make a fraction out of it by putting -5 over 1, so that means it qualifies as being a rational number. Since we can make a fraction out of it, it's definitely not irrational, but it is real. Remember again, all of these guys belong to the real numbers. Okay, well, as a next example, let's take a look at, for instance, 17/12. Well, this is not something you'd run into in counting something, and it's not a whole number either. And of course, the integers don't have any fractions with them. They just have positive and negatives, but no fractions. But it is a rational number because rational numbers can be written as a fraction, and here we go. So it's rational, and since it's rational, that means it's not irrational. We can write it as a fraction, and the irrationals cannot have that happen. And of course, it's a real number. So 17/12 just qualifies for 2. Okay, let's take a look now at 4.5. Again, you would not bump into this counting things, and it's not part of the whole numbers either. There are no decimals in whole numbers, and of course there are no decimals or fractions in the integers, so it's not that. But when you get to the rational numbers, remember that a rational number, besides being written as a fraction, can be written as a decimal if it terminates or repeats. Well, this one terminates right here in the tens place. So that means it's definitely a rational number. It's not irrational. Remember, irrationals, decimals go on forever. This one terminates. But of course, it's also a real number. Okay, next example. Well, this is a giveaway. Our classic example of pi. Remember, pi was the value that drove the Greeks nuts, and it's a classic example of an irrational number. If you were to try to calculate its value as a decimal, it would go on forever. So it's definitely irrational, but the irrational numbers are still members of the real numbers. So pi is irrational and also real. Okay, our last example is looking at square root. Now, the first thing you do when you have square roots is see if it has a nice answer. If this was the square root of 9, the answer would be 3, and it would be a rational number. But the square root of 26 does not have a nice answer. It's got a decimal value that'll just keep running on forever. So because of that, it's an example of one of these irrational numbers again, just like our friend pi. But it is still, of course, a real number, so we have to list that as well.